Okay, let's dive right into this. We're talking about forces on an absolutely colossal scale. I mean, just picture a massive oil derrick that has to lift equipment weighing hundreds of thousands of pounds from way deep inside the earth. You gotta wonder, how is that even possible?
Yeah, that's really the central question here, isn't it? How do you lift 300,000 pounds? We're talking the weight of a blue whale, with what is, basically just a single steel cable. It sounds totally impossible, but this is an everyday thing out on the rig. And the way they do it, well, it's a total masterpiece of engineering.
So, to get our heads around how this works, we need to meet the three main players in this whole hoisting system.
First up, you've got the derrick. Think of it like the giant steel skeleton of the whole operation. Its main job? To give you all the height you need to pull these super long 30-foot sections of pipe out of the ground. But it has another equally important job, to somehow withstand just incredible forces.
Then there's the drawworks. This thing is pure muscle. It's basically a giant winch that spools that steel cable, giving you all the raw power you need for the lift, and, just as important, the brakes you need to lower everything back down safely.
And finally, we have the block and tackle. This is the real secret weapon. It's this clever system of pulleys that takes all that raw power from the drawworks and actually multiplies it. This is what makes that impossible lift, well, possible. Okay, so how on earth does this system multiply force? Well, it's not magic, even though it kind of feels like it. It's pure physics. The principle at work here is called mechanical advantage, and it's basically a fancy way of saying you're making it a whole lot easier to lift something super heavy. So check this out. If you just have one fixed pulley, all you're doing is changing the direction you're pulling. No real advantage there. But the moment you add a movable pulley, like you see in step 2, things get interesting. The load is now split across 2 lines of rope, which literally cuts the force you need in half. That is mechanical advantage. And in a full-blown system, the load gets divided among all the different lines running between the blocks.
Now, the rig we're looking at here, it uses 8 lines. So in a perfect, frictionless world, that would divide our 300,000-pound load by 8. That means the drawworks would only have to pull with about 37,500 pounds of force. Pretty amazing, right? But, and there's always a but, the real world has a catch, and that catch is friction.
You see, every single pulley in the system creates friction, and that friction forces the drawworks to pull just a little bit harder than that perfect, ideal calculation says it should. So engineers have to account for this. They use something called an efficiency factor. For a system with 8 lines, for example, the efficiency is usually around 84%. That means you're losing about 16% of that perfect mechanical advantage just to friction.
Okay, so we've got a handle on how the lift works now, and it seems pretty logical to think that the derrick structure itself, well, it just has to support the 300,000 pounds that's being lifted. I mean, it's just holding the weight, right?
Not even close. And this is where the engineering gets really interesting. Because you have to remember, the derrick isn't just holding up the payload, it's supporting the entire pulley system that's doing all that heavy lifting.
This means we have to start thinking about all these hidden stresses. The derrick isn't just some static hook hanging from the ceiling. No way. It's an active part of this whole pulley system, and that means every single part of that system is pulling down on the structure.
So the actual total load on the derrick is really the sum of 3 different forces all pulling down at the same time. You've got the hook load itself, obviously. Then you've got the fast line. That's the one pulling towards the drawworks. And finally, the dead line, which is anchored right to the rig floor. But wait, it gets even more complicated. Because of where the drawworks and that deadline anchor are actually positioned on the rig floor, that huge total load, it isn't shared equally by the derrick's 4 massive steel legs. It actually creates a dangerous imbalance. And this imbalance is absolutely critical. In fact, as one engineering text puts it, because of the rig's geometry, and I'm quoting here, leg A will be the most loaded leg, and very likely it will be the first to fail. Think about that. That one specific leg becomes the weakest point in the entire structure. So, how do you design something to handle such an intense, unbalanced force? Well, engineers have a strategy. They design for the absolute worst-case scenario. They use a really important safety metric called the equivalent derrick load, or FDE for short. What they do is calculate the intense load on that one single most stressed leg, and then they multiply that number by 4. This basically rates the derrick as if all 4 legs were under that same insane amount of stress. And that final FDE number, it can never be higher than the derrick's official maximum capacity. Let's go back to our 300,000-pound lift. The numbers here are pretty revealing. The actual total load on the derrick is around 341,000 pounds. But that critical safety number, the equivalent derrick load, is almost 385,000 pounds. That is nearly 30% more than the actual weight they're trying to lift. The hidden forces at play here are just immense.
It's really a breathtaking balance of clever physics and just brute strength. But it kind of leaves you with a final chilling thought, doesn't it? In a system that relies on such massive forces and such precise calculations, what happens when just one of those numbers is even slightly off?